Hi, thanks everybody for turning up. Thanks for inviting me to talk here. My talk is on GPS technology, so a few simple questions first. Hands up if you know what GPS is. Cool. Hands up if you use GPS to get here. Ooh. A pilot or a driver use GPS to get you here anymore? Hands up if you think GPS is a great tool. Hands up if you think GPS is a great tool for a surveillance state. Hands up if you already think it is a tool for a surveillance state. Okay, so what's that, about a third of the audience? Hands up if you know of how it works. Ooh. Cool. So I'm Mike. I'm a C programmer since the 1980s. Linux user since OS2 Warp disappeared in the mid-90s. I play with FPGAs and microcontrollers by evening. In the day, I'm a SAN administrator for a local cloud services provider. I still occasionally come out of retirement and pull Linux tricks out of my bags to recover buildings which have burnt down or recover failed RAID arrays. So for this talk, you can expect to get some insight into how GPS works at the very lowest levels. I've got a picture of a few commonly available GPS modules, a few slides on how you can connect a GPS module to a Raspberry Pi, and a little bit on the stream of data coming from the module, and a rapidly growing section on the security issues for GPS. So as long with the happy penguin, we have a sad panda. And I won't be talking ethics. I won't be interfacing to any web services other than maybe a cut and paste. There'll be very little information on using GPS as a time reference. I know very little about the other GPS-like systems, and my slides are particularly not too flash. And just as a word of caution, everything here, first approximation, there are lots of finer details. They're not really that important. A lot of things in GPS have changed over the last 20 years, so some older material is no longer applicable, but I haven't got that in my slide, but you may run into it. And I've thrown away half of my slides, so there may be bits of patches missing. What is GPS? GPS is a global positioning system, or GPS is a global navigation satellite system that allows you to work out where you are independent of anything else in your environment. So as long as you can see the sky, you can put a pin in a map and say, I know I'm exactly there. There's quite a few other global navigation satellite systems, but the Navstar GPS was the original, and that's what everybody thinks about when they talk about GPS. It was made in the USA with global materials. It's owned and run by the United States government, which most probably means United States military, and there's 33 satellites in orbit around the Earth. They're in semi-synchronous, so rather than hovering over one spot, they go around the Earth twice a day. No, they go around the Earth once, but the Earth is rotating, so there. You can own a receiver for a few dollars, but it costs nothing to use one. Completely license-free. Buy the hardware, it's yours. Do what you want with it. How accurate is GPS? This system design is designed to be accurate within 10 meters, but not all the time. If you're looking for time accuracy, it's about 15 billionths of a second, which is pretty accurate. Briefly, how does it work? Trilateration. So everybody knows triangulation. You have 2 points and 2 angles, and where the lines cross, you get the third point. Trilateration, you have 2 points, 2 fixed lengths, and where those lengths meet gives you your third point. Wikipedia says it much more precisely than that, but the general idea is you need reference points, you need lengths. So for GPS, you measure lengths by the time that a signal takes to travel through space. If you know how long it has travelled, you know how far it has travelled, and with 4 of these lengths and 4 reference points, you can work out where you are in 4 dimensions, X, Y, Z, and time. The entire GPS system consists of 3 parts. There's a control segment, which nobody really knows much about unless they've actually studied GPS technology. There's the space segment, everybody knows that, the user segment, the end device. So the control segment is a whole lot of base stations spread across the world, including one here in New Zealand. They make recordings and monitor the positions of the satellites and then act as a feedback loop to say, hey, this satellite's drifted a little, change these numbers, do a little bit of tweaking. They also have to analyse the satellites if they make any orbit changes to stay on station. Yes, there's quite a few of them spread all across the globe. Once you start looking in detail, you start realising, well, actually, these are moving as well with continental drift. I haven't really looked at it, but it must be pretty hard to work out where these points are so that you can survey where the satellites are. A very low-res picture of the space segments. There's 33 space vehicles, approximately 26,561,660 metres from the centre of the Earth. Yeah, well, they're not that well known. They transmit with about 25 watts of power. So each of those transmits covers the whole globe. So the blinking LEDs on the little satellite there, that's about as much power would hit the the whole of New Zealand. The signal's really, really weak, and if you've got a little antenna that big, it's below the noise floor. And here's a picture of a actual GPS satellite and a little diagram showing just how far away from the Earth the actual orbit is. Finally, the user segment, what everybody calls their GPS. It's a cell phone, a little Arduino GPS module, or your self-driving car, your survey equipment, your agricultural equipment. These receivers only listen to GPS, and by analysing the signal, they work out where they are. It's not as though the space vehicles are tracking you, you're tracking them. So that's the parts. How do they all fit together? How can my little GPS receiver know exactly where satellites are 20,000 kilometres away? The space vehicles, this is a diagram of a very early GPS satellite, send out 2 main signals, one of which is military only. The other one is a composite signal of the carrier and 2 different codes which get merged in on top. There's a CA code, which is used to find a satellite, and then there's navigation messages, which is actually a data stream. It's sent at 50 baud, so it's very slow, very old. Each of the space vehicles transmits its own 1023-bit binary number at 1.023 megabits a second. This is exactly the binary number transmitted by Space Vehicle 01. To send a 1-bit, it sends this code 20 times. To send a 0-bit, it sends the binary inverse 20 times. It's pretty much as simple as that. When you multiply a carrier signal by a set of random numbers, all the frequencies get jumbled up and it generates a spread spectrum signal. What happens is all the power in the carrier gets smeared out across the whole bandwidth, but the process is reversible. If you put the same random or pseudo-random bits, you can push all that power back into a single signal and you can find the carrier again. The trick is you have to have the same bits played back at the same time. Because the different satellites use different sets of the 1023 random bits, they can all transmit in the same bandwidth at the same time. If it's not the satellite you're looking for, its signal just gets even more blasted apart into noise in the bandwidth. We have a slight complication. Unlike these guys here, in space they're moving around at 14,000 kilometers an hour. This causes their carrier signal to wander a little bit. As they're coming towards you, they're a little higher pitched. As they go away, they're lower pitched. You have to look and try and find where these satellites actually are. So if you don't use any advanced techniques, it can take approximately 1.5 million attempts to find all the satellites which are in the sky. You have to look on 21 different frequencies at different alignments of their code for 32 different satellites. It's a lot of work. There is shortcuts which can do this quicker, but they're not commonly used. So if you wanted to build a GPS receiver, the first thing you need to do is actually see if a satellite is in the sky and try and acquire it. Up the top we have a carrier which has been modulated by the code the space vehicle uses. And as long as you are within a microsecond of the true alignment of that code, you can then pull back out the original carrier and you have some received power. If you're not exactly aligned, like if you're half a microsecond off, you'll see some of the signal. If you're half a second early, you might see approximately the same amount of signal. But by tracking those 2 points, you can actually work out what's the best alignment and actually lock onto the signal. So I mentioned previously that every 50th of a second, the space vehicle can change from sending a 0 to sending a 1. So when we have our received carrier at the top, we can then compare it to a local reference. We can then recover the actual bits being sent. This happens sort of at the millisecond level, whereas looking at for the gold code happens at the microsecond level. So this is a dump of data put into Excel of an actual satellite signal being received. We've just had a sniff at the power at the left-hand side. For the first eighth of the screen, it's trying to lock onto the carrier frequency, and then after that, in the red line, you can clearly see the data bits coming down. So that looks to be about 1.5 seconds worth of data. The graph below is sort of the control system, well, the feedback loop, trying to lock onto the carrier frequency. So the nav data comes down from the satellite at 50 bits a second. This is pretty much what it looks like. It's just a whole lot of floating point numbers describing the orbits of the satellites, allowing you to predict where they will be and when they will be there. It takes 30 seconds to receive a full set of information from a satellite, as well as orbit. There's timing information, and then there's, what's the word? A cut down set of information on the positions of the other satellites. So when you find one satellite, it gives you hints how to find the others. So you've got this running, you're tracking 4 satellites, you then want to actually work out where you are. You take a snapshot of the state of the receiver. Where you are within the magic 1023-bit code gives you your time within sort of 10 nanoseconds resolution. Then where you are within the 20 millisecond bit gives you your approximate, well, your exact millisecond resolution. Where you are within the frame gives you even more 20 millisecond resolution, and then so on until you know exactly what week, exactly what frame, exactly what millisecond, down to about 10 nanoseconds. So we can then put the location of the 4 satellites, what we understand the space vehicle's local time to be, a guess of the receiver's position, a guess of the local time, into a big matrix and solve it as a linear equation. So this is actually the code. I didn't write it myself. I borrowed somebody else's to the magic of open source. So out of this equation pops your approximate location. We have problems. When a radio signal comes through space, it travels at the speed of light. When it hits the ionosphere, it slows down a bit. When it hits the atmosphere, it slows down even more. Depending on how high the space vehicle is in the sky, it'll slow down by different amounts. So you then have to work out, given this approximate location, where are the space vehicles in the sky, what correction factors do I need to apply, and then you can feed it all back into the same linear equation and solve it a second or third time until you get a stable result. And then you end up with a fix of where you are. So I just have happened to have written a complete software implementation of a GPS receiver. So we've got this file, GPS data with a timestamp on it. This is raw samples coming out of a RF head end of a GPS receiver. And so we're just about to do receiving. Up the top of the list of space vehicles it's trying to acquire. Below that we have a list of the state of the receiver with what space vehicles are being received, their power levels, what they think the local time on the space vehicle is, and how many errors there is in the data feed. In the middle we have the space vehicle positions. As soon as enough is known to say where the space vehicle is, that'll pop up in X, Y, Z and T. And hopefully, fingers crossed, but since it's using a sort of canned data set, I know it'll work. Down the bottom we have the solution for position in a couple of different formats. And I can see that my font is too big, but it won't matter. So we'll set it going. So I was a bit slow, but after 9 seconds, it thinks it's got 6 possibilities of a satellite, 4 of which look pretty good, 2 look just to be random noise. The next thing that'll happen will be the frames will start being received. So where it's got 5 dashes, it'll count up 1, 2, 3, 4, 5 as it receives the different frames. And then we should get positions in the sky. So we've got frame 1 and frame 5 for one satellite and frame 1 for another 5. Cool. So we've now tracking 5 satellites. We've got positions for 5 of them. And down the bottom, we've actually got a workable solution in lat long and altitude. We'll leave that running. So this is all running on a single core. It runs faster in real time. It's pretty practical to do a software-defined GPS receiver. So hopefully, or I don't think that'll matter. So this is about as much. Ooh. I do have Chrome open. Where are you? As much web integration as I'll do. If launch Earth in Chrome. Apologies, I did have it running in another window, but it seems to have got upset. So that's the solution cut out of the GPS receiver. And hopefully you'll find where I used to live a couple of years ago. Done. So we actually used to live here, and that data set was recorded on the back porch. So close enough. So that's the ultra geeky stuff out of the way. Now onto the rest of it. So, positioning accuracy. 95% of the time, it should be within 10 metres of your true position. Close enough for jazz. If you need better than that, you can use satellite-based augmentation systems. There's actually been a trial of this running in New Zealand to see the benefits for industry and aviation and so on. You rent bandwidth on a commercial satellite in geostationary orbit. You transmit down correction factors because the major source of error is the uncertainty in space weather and the atmospheric conditions. With a space-based augmentation service, you get accuracy to about 1 metre, which is close enough to land aircraft. It's actually cheaper to implement a space-based augmentation system than to do precision, install the equipment to do precision landings at airfields. I think it's about, if you have to upgrade 5 airports, you're better off doing this. So that'll happen. The other thing you can do is you can record the state of the GPS receiver, and then you can analyse it offline later when there's more certainty over where the satellites were, what errors were in the system. It's called precise point positioning, and it can give you accuracy to about 10 centimetres. So it's used quite a lot in survey and geological, what's the word, geophysics. It's not so much used for surveying land lots or anything like that. They tend to use steel pegs. Maybe 10 centimetre resolution isn't enough for you. You can use real-time kinematics. You put a second receiver, you hold it stationary over a known fixed point. It experiences the same errors as a mobile receiver in the same general area. If you transmit those errors over a radio link or the internet or any other sort of mobile data service, you can then null the errors out again, and you can get accuracy down to 10 millimetres. This is why when you see surveyors out in the street, they always have a tripod with a box on it doing absolutely nothing. That's their reference point, and then they wander around with a stick with the second receiver on it. Close enough for tractors and surveyors. So here's a graph of relative accuracy. It's a logarithmic scale on the left, or on the Y, just in case that trips you out, and pretty much shows how all the different, the relative accuracy of the different systems. One slightly good thing maybe is that augmented GPS is going to be an enabling technology for self-driving cars, so the modules should be cheaper, and the price of that should come down. So I did an experiment. I got a module, connected up to a microcontroller, left it on the front windowsill for 2.5 days, and then I've come back and plotted the fixes. There's 200,000 points plotted on here. As you can see, most of them are in a tight cluster. However, sometimes they wander off into the middle of nowhere. It's fine if you're just, on your front windowsill, but maybe not so good if you're flying a drone or something like that. Current drones have a camera on the bottom and take a photograph when they lift off, and so when they come back, they get into the same general area and then can use the image to land exactly where they came from. So, yeah, not so bad. A lot of these errors happen when satellites go in and out of view, and it has to change which set of satellites it's using to make the solution. Timing accuracy. GPS modules have a pulse per second signal on it. It's usually accurate to, well, it can approach 15 nanoseconds. On the cheap modules, you don't get anything like that. If you were to use a module, the pulse per second signal is the reference point that will be asserted, and then a short while later, across the serial data lines, it'll tell you what the timestamp is. the timestamp isn't actually aligned. The timestamp you receive down the serial data feed isn't actually accurate. So I did another experiment. I recorded the count between the rising edges of a receiver's pulse per second signal for 10 hours, and this is what I got. So it varied by about 1 part per million. So it sounds a bit bad, but it's approximately the height of an M&M on top of Mount Cook. So if you use that to calibrate your watch, just the interval between 2 of these pulse per second signals, you'd be out by at most 8 seconds in a month. Of course, if you continuously corrected to the pulse per second signal, you'd still be accurate to within a microsecond after your month. So, a cautionary tale. So, part of me was thinking, yes, this is an innocent mistake that somebody uploaded bad data into the GPS satellite vehicles and causing a time glitch. Yeah. It glitched by 13 milliseconds. It took a whole lot of radio observatories down. A whole lot of financial institutions found that their transaction logs jumped backwards, caused a bit of hassle. So, easy fun bit. How do I use GPS? It's almost child's play. Grab a module. Oh, it's already got an antenna on it. Here we go. Grab a module, grab an antenna, grab your, connect it to your compute platform. I hear quite a few people have Raspberry Pis, piece of cake. Receive data from your module. So here's a selection of modules, inexpensive, $5, usually with free shipping from AliExpress. It's, cheap as chips. Antennas are a little bit more tricky. They have to be able to see the entire sky. They have to be small because after all you are using them as a position reference. And we also want them low cost. So there's a couple of sorts. Well, actually, this picture is the received signal strength from an antenna on a front windowsill. Also shows how much of the sky the space vehicles are in, somewhere near Christchurch. So, very small patch antenna, piece of cake, really great for experimenting with, absolutely no value for anything really because your board gets exposed to the environment. A bit better is a lot better is an external active antenna. Once again, under $10 with free shipping, and you can then put your electronics away somewhere nice and safe. If you're using them as a time reference, it does take a while for the signal to get down the cable, so you have to, correct that on the way through. How do you connect a GPS module to a Raspberry Pi? Connect 3 wires, power, ground and signal. About 4 Unix commands to set up the serial port to check if anybody's using it. Turn off the Getty, which is always running on Raspberry Pis. Give yourself access to the port and set the serial baud rate. Then you should be able to get data from your module. All GPS modules transmit in the same data format. They're called NMEA sentences. I think it's National Marine Engineers Association. It's a standard for navigation equipment. Here's one of the sentences. They all start the same with a $sign. The first field is the type of sentence they are. At the end they have a star, and then they have a checksum. You X all the characters together between the dollar and the star, and it should equal the checksum. Goes without saying, always verify the checksum before you use the data. And then you can break the signal down into individual fields. Nothing particular flash here, except one trap is that the latitude and longitude isn't decimal. It's a bit like hours, minutes. It's a bit like hours and minutes, but without the colon between them. So the first 3 digits are the degree, the next 2 are the minutes, and then fraction of a minute. There's also lots of other good things like speed and true course, time and date stamp. And so here's a sentence decoded, a little bit of math, and you can work out where you are, cut and paste it into Google Maps. There's a whole lot of other sentences as well, which can give you a better view of the information you're after. Usually, if you wanted to do, say, a GPS-enabled speedover on your Lime scooter, you'd most probably look at the speed over ground message rather than the position and do funky math to work it all out. Oh, working with geolocation data can be hard. So, a helpful measurement to remember is that pole to equator is 10,000 kilometres. I think the definition of the metre is 1/10,000,000th of the distance from the North Pole to the equator when going through Paris. After a while, you sort of can look at the numbers, see if they're just about right. Latitude and longitude can be hard to work with. Longitude wraps around, latitude bounces when you reach the pole. Once you go north, you can't go anywhere. Once you get to the North Pole, you can't go more north. Doing maths can also have a few tricks. Going between 177 degrees west and halfway between 177 degrees west and 179 degrees east is 179 degrees west. Scratch your head a bit. So when working with GPS, it pays to think a lot about what coordinate system you'll be working in. Flat Earth, spherical, ellipsoidal, I think I've said that right, or Cartesian. Getting this right or using multiple coordinate systems at the same time can actually make things a lot easier and a lot easier to get accurate at the first time. So in a flat Earth, we assume that a degree of latitude and a degree of longitude are much the same. It's great if you just want to record the position you're at, but it only really works at the equator if you want to do math on between two locations. If you're doing math on a town scale or maybe up to 5 or 10 kilometres, you can just scale the longitudinal distances, so the distance from east to west, you can scale them by the cosine of the angle of latitude. Great for calculating speeds. You could get across Christchurch and still be, pretty close to where you are. Only becomes a problem as you get very close to the poles and, the accuracy quickly falls away. So, a spherical Earth. Assuming a spherical cow. It's an old physics joke. Worst case error is about 0.1%. The next thing up is to use the reference shape for the Earth, which is WGS84. Really hard, but that would be the reference shape that people who are actually doing surveying would use to get things right. And finally, you can get Earth-centered, Earth-fixed, which is XYZ, just like computer graphics, and there's a few funky formulas which you can use to convert between the two. It's the internal coordinate system used by GPS receivers. If your receiver can give that data to you, it's most probably easier to work with. Cool. So, audience participation, security of a GPS system. Perfect. So, I've got a few news articles. Goes without saying that you can cut off your GPS home detention bracelet and walk away and walk around. This is more amusing. Bracelet flaw allows home detention people to wander free. Wrap it with a roast chicken bag. This is panic-inducing. Jamming. You transmit another signal on the same frequency. The signals are so weak you can wipe them out. Somebody got fined €2,000 for leaving his GPS jammer on parked at an airport. Yes. So spoofing. This is when you transmit a signal, which looks to be a valid signal, to a GPS receiver to get it to do things you don't, well, things you want the person to do, but they may not want to do. There's a whole lot of research on this. It's all really interesting how you can transmit at low power levels, slowly ramp up the power to take control of the tracking loops in the receiver, drag them to the side, and then drive people into walls. You can do firmware attacks as well against the firmware in the receiver. So this isn't attacking the code in the receiver. This is supplying bad data to the receiver to get the firmware to do bad things, hopefully just crash the module, deny data. You can lose control of your data. So may not be the best if your soldiers in Afghanistan publish where they are on a heat map for Strava. This morning when I got up out of bed, I realised I had forgotten 3 other things. You can attack the GPS system itself. There's nothing which stops the GPS satellites from saying, hey look, my messages are bad, ignore me, GPS could go away. Might be unlikely to happen, but who knows? Who really knows? I wonder what a military receiver would do in that case. It's conceivable that all military receivers will go, hey, if you see all the space vehicles go offline, we're just kidding. You know, still land the missile where you want it to go. You have state-level actors. They can launch balloons, high-altitude balloons. They can launch rockets. You have geopolitics, which we may get into a little bit later. You can have space weather. Another solar flare like the one in 1859 would most probably disable GPS and any system which relies on it. And last of all, you have the navigation paradox. Better navigation precision is not always safer. So what's more likely here? Did 2 people put the same destination into their GPS system, or did they get hacked? I think 2 US Navy vehicles crashed into each other in the Black Sea. Yeah, I think I'm purely on the fence on that one. It has been shown that in the Crimean Sea there is GPS oddness going on occasionally when there's military activities. Cool. Any questions? Sir?
I shall start again for the benefit of those watching at home. If you're in a situation where you're somewhat indoors, but you can still get signal coming in the windows, how hard would it be to make a receiver that can correct for the distance in from which direction the different satellites might be getting picked up to try and correct for some of that?
So there's 2 issues there. One is multipath, where a signal reflects off a foreign object, comes to you by a longer path, and you get a blurring of the receiving, making it harder. A lot of receivers can detect multipath and adjust for it, but the receiver itself has no way of working out that you're indoors and my signal, or you're down a well or something and my signal is travelling so many metres further than it should. You're just, you have to have a clear vision, a clear view of the sky in case if you want to see it.
Cool.
As an example, staying in a hotel in Wellington on the north side of Lambton Quay, my receiver told me that I was at the Poke stop on the south side, which was really quite helpful.
Yes.
Just wondering, do you think it would be possible to use some of the newer SDRs which use coherent antennas, so for example 4 antennas, to measure also direction of the signal to improve the precision of the GPS? So
the precision problem isn't direction related, it's more allowing for local issues. I think about 85% of the error in GPS is caused by ionosphere or troposphere effects. The way it's actually accounted for in better receivers is they receive the L2 signal, which is on a different frequency. It slows down differently as it travels through the ionosphere and through the atmosphere. And then by having a look at the difference, you can then say, great, I know that this signal is this much slower than that one, therefore that's the error. So the actual direction doesn't help, and you've still got the problem, not so much if it's a phased array, but you've still got the problem that you have to receive it at a point to get a useful point reference.
Any more questions?
So if there's all of these strategies to correct for errors down to quite a small margin of error, what's the benefit of the alternative military channel then? Is there some other gain that they get beyond accuracy?
So,
Obviously we don't necessarily.
yeah, no, the original system, the CA signal we used was just used to find the satellites. It was to make the problem easy enough that you could locate the satellites and then switch to the other military-only code. And then they have two frequencies so that they can adjust for atmospheric effects. What they didn't realise, or didn't take into account, was the progress in receiver technology and digital technology, digital signal processing. Not only can you receive the CA and get it down to such a fine resolution, but you can also sniff sort of side channels of the military information and actually not access the data but use the timing information it provides, which is those are the receivers which cost hundreds of dollars as opposed to just a handful of dollars.
Any more? In that case,
Oh, by the way, if you want a satellite, go grab them. They're running MicroPython. I've got an extra couple if you're panicked.
So you talked a lot about GPS. Are any of the other GNSS systems of use or likely to be more important in the future?
I've had a look at a couple. The actual technology isn't that different. It's that they use more advanced data protocols and better error correcting and better framing protocols. For example, the Indian one, I can actually receive and prove that the signal is there. I just haven't done the work to splitting up the frames to give the navigation data where you can make use of it. The other problem is they're on a different time base. So if you use GPS, that time's only relevant for the GPS navigation information. You can't go, oh great, I've got 5 GPS satellites and this from a different constellation. You can't use that foreign data to improve your solution.
okay, if that's all the question, I think I'd just ask you to show your appreciation to Mike again.